Okay, we want to talk about how to get an estimated quadratic fit. Of course, your calculator will do any kind of a fit. Well, calculator has all kinds of fits. If you decide that a straight line isn't a good model here, this thing is basically got a shape something like this, then you draw a curve that you think does a pretty good job of representing the function, and you conjecture that maybe this curve is quadratic. So what you do is you take 3 points on the curve. Okay, so I'm going to take the point where y equals 128. It looks like x is about 14. So I'm going to use this point here, 14. My comma would become the 2 in my 28. 14, 128. Okay, and I'm going to do a point down here where it looks like x is about, that's 48, that's 64, subdivide again, that's about 51. 32, subdivides, that looks like it's probably about 28. And a point somewhere in the middle, maybe right about here. So I'll come down here, and subdivide, there's 24, there's 28, that looks like about 26. And come across here, subdivide again. It looks like it's about, where am I? My subdivisions are each going to be 8, so that's going to be 72. It's going to be a little less than 70, say about 70. Okay. Now you might want to make your estimates a little more carefully if it's important to do so. This gets across the idea. Okay, so now we've got 3 points. Now why do we want 3 points? It's because a quadratic function is of the form y equals ax squared plus bx plus c. Okay? And we have 3 parameters, a, b, and c. Just like with linear equation, we had 2 parameters. The first one we did with a standard form, whatever, the intercept form actually, was ax plus by equals 1. Okay, we solved for a and b. We had 2 simultaneous equations, 2. I'm going to spell up 3 fingers because I'm still thinking this. Okay, well, each point has an x and a y coordinates. If we plug in the y coordinate here and the x coordinate here and here, we get an equation. Right? That's a nice linear equation with unknowns a, b, and c. We call these parameters a, b, and c. So the first point gives us y, which is 128, equals, well, it's a times x squared. X is 14. Everybody knows 14 squared is 196. That's 196 x, 196a. And then bx, well, it's going to be 14 times x, not 14 times b. Okay. My turn not to quite get enough sleep last night. Okay, hope everybody else did. And then plus c. Similarly, second point, 2670. Okay, y is 70, so we put in 70. Okay, 26 squared. What's 26 squared? 25 squared, 620, must be 676. I hope that's right. That's plugging the 26 in for x here. We got a square. 26 plugged in here gives us 26b plus c. Down here, 5128. So we'll start with the 28. I'm going to have to square 51 here in a minute. Okay. Now 51 is 50 plus 1. When you square 50 plus 1, you get 50 squared plus 2 times 50 times 1 plus 1. Okay? And that would give me 2601. Now I'll write that down. because it's handy to be able to do this. 50 plus 1 squared. I mean, you have a special formula in algebra. A plus b quantity squared is a squared plus 2ab plus b squared. You get that by multiplying a plus b times a plus b using the distributive law. So you could use that formula, or you just use the distributive law. 50 plus 1 times 50 plus 1 is going to give you 50 times 50, which is 2,500, plus 50 times 1 plus 1 times 50 plus 1 times 1. Should have written that as 50 times 50, but now if you write it 50 plus 1 times 50 plus 1, then apply the distributive law twice. This is what you get. And that's 2101, 2601. Okay, so that's why I wrote 2601 there. And then plus 51b plus c. Well, now that's 3 simultaneous equations. What are we going to do with 3 simultaneous equations? In this case, it's actually pretty easy because all the c's have coefficient 1. So I can just subtract the first equation from the second. Okay, now the number with the circle around it refers to the equation, the number of the equation in order in the previous step. But the second equation minus the first. Now I'm going to switch gears and put the expression with the a, b, and c on the left and their number here on the right. So I'm kind of reversing these equations. Hopefully that's not confusing. 676 minus 200 would be 476, but I'm only subtracting 196, so that's 480. And I could make a mistake here, so as I say, keep an eye on me, check my numbers. 26b minus 14b is 12b, and c minus c gives you 0, and that equals 70 minus 128, which is negative 58. Then we could do equation 3 minus equation 2, or 3 minus 1. The numbers in 1 are smaller than numbers in 2, so it's going to be easier to do this in my head and hopefully without an error. But I could as well do equation 3 minus equation 2. I just have to use 2 different pairs of equations and eliminate c, and hopefully you see what's emerging. I'm going to end up with 2 equations and 2 unknowns, a and b, because c is going to be gone both times. Okay, so 2601 minus 200 would be 2401. I'm only subtracting 196, 4 less, so that's going to be 2405a, plus 51 minus 14 is 37, that's 37b, and that's going to equal 28 minus 128, conveniently negative 100. Now I'm down to 2 simultaneous equations and 2 unknowns. I'm not going to solve this. Okay, I'm going to have to multiply by some pretty big numbers. Like I would choose probably to multiply the first equation by negative 37 and the second equation by 12. Then I would have negative 37 times 12b and 12 times 37b. I'd have equal and opposite numbers, so when I add the 2 sides, b goes away, I end up with an equation in a. And again, this is something I assume is familiar. You might not have had to do it with numbers this big, but you just use your calculator. And I do, don't expect you to do these in your head. Even if you can do some of the arithmetic in your head, if you can, you should, and then use your calculator to confirm it. Like I didn't do, so I probably have a mistake in here somewhere. Okay, so, but we then, we add multiples to eliminate b, and solve for a, then back substitute. Meaning, once we get a, down here in this step, we plug it into one of these equations. It'll just be a number, so we'll be able to solve for b. Then we'll have a solution for a and b, and we can put it into any one of these equations. Probably the first one, because the numbers are smaller. Okay, so we put in numbers for a and b, and we'll be able to solve for c. then we're going to have our quadratic model. We're going to have y equals some number times x squared plus some number times x plus some number. And if we plug in the coordinates of any one of these data points for x, the y that we get should be pretty close to the y that we observed in our data. And that's the process. That's another kind of simultaneous equation that we use for an exponential or a power function. We'll go over that.